Okay, kids. Let's do a very quick, simple lesson to get back into the flow of things. Haha, what a great joke. Okay, so hopefully you remember the concept that voltage is energy per charge or work per charge or change energy per charge. That's a good equation to know, but the concept is really important. It's a potential difference. Potential difference is the difference in energy held by charge at one location compared to another. So in physics, potential difference or voltage is always caused by batteries. We talked about like the outlets in your house with like the two prongs, but for now we're talking about batteries. And basically, charge can come in, charge flows out of the battery, but it also flows in the other side. It's the same charge. It could be the same like 2 coulombs of charge, but the difference is that the charge flowing out the high voltage terminal has more energy. The charge flowing in has lower energy. Some people like to say positive terminal, negative terminal. Not really correct. Don't say that. I'll come back to all this later. But basically, charge will come out of one end of the battery and it'll go back in the other side. This flow of charge is known as current. Current is symbolized by I, and it's measured in amps. So maybe the current, let's say I have a 12-volt battery, and I have some stuff we'll talk about tomorrow. Let's say it gives me current of 2 amps. Or an amp is a coulomb per second. So just like a speed is measured in meters per second, a current, an electrical current, is measured in coulombs per second. You probably know that like there's electrons flowing and they're bouncing around inside atoms, and there's like a sea of shared electrons and all that other fancy stuff. But we don't care about that. We don't care about the number of electrons. We don't care about the speed of electrons. We don't care about the mass of electrons or the path of electrons or anything like that. All we care about is the total charge. The total charge that flows through a point per second is the current through that point. A really important concept. It must be the same. The total current going in and the total current coming out of any object. I'll draw a mystery object right here. This mystery object will have the same current coming in as coming out, and that will be the current through that object. So instead of Q for charge, if we know how much time it takes charge to flow, we can divide the charge by that time to find the current. So if 10 coulombs flow through my mystery object in 5 seconds, then that would give me a current of 2 coulombs per second, or 2 amperes, or 2 amps. Ampere or amp is fine. Amp is pretty much more common. Okay, a couple things to clarify. Let's go back to the river analogy. Let's say you're building a nice house to a nice mill to grind some grain in. And you have a big mountain with lots of snow and nice flat ground, and then a nice lake. That's what lakes look like. All right. Should you build your water mill, your mill in the bottom of the lake? No, Mr. Lamb. Why not? Because inside the lake, the water's not moving. Yeah, that's right. You wouldn't want to build your mill underwater at the bottom of the lake. You should instead build it at the top of the mountain. No, Mr. Lamb. Why not? Well, there's no water at the top of the mountain. The water here is all in the snow. It's melted. It's frozen solid. It's not moving either. This is liquid water, not moving. This is solid water, also known as ice, which is not moving. So where should we build a water mill so we get the best flow of water? Right in the middle. Yes. If you want to build a nice water mill, you need like a much better. And then pew 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 pew. A great drawing for a great lesson. Here's my water mill. You need to have some kind of river. So maybe if you build your mill here, you can dig yourself a channel, dig yourself a river, and water will flow down the mountain right past your mill into the lake. You need to have a flow of water. Just water doesn't power your mill to grind your wheat. You need water to be moving, to be flowing from high to low elevation, from the mountain to the lake. The flow of water is like current. In fact, if you just say current, you could be talking about the flow of water because, like in the ocean or in the river, you can feel the water current. Current's the same word, current, current. So this is water current. This is electrical current. We need the same amount of water flowing in as flowing out because otherwise something bad will happen. For instance, now. So, you need the same water coming in as coming out to your mill. Otherwise, you're going to flood your mill or you're going to run out of water. Both are bad. And the flow is caused by this elevation difference, this potential difference. Water, let's say I have 1 kilogram of water. 1 kilogram of water has much more potential energy at the top of the mountain than it does at the bottom of the lake. So, when the water flows, the water comes in and the water comes out. It's the same water, it's the same amount of water, just the water has less energy. It gave the energy to you so you can like grind some bread, grind some grain, make some bread, and have a great life. So that's basically what's going on here. We have a battery. There's a high voltage terminal and a low voltage terminal. People always write or draw plus and minus. It's not positive and negative. Don't think that. It's not like you rubbed a bunny on this side and like a rubber rod on the other side. Nothing like that. It's just one happens to be higher voltage than the other. We don't care why. We don't care what was rubbed or what was transferred or where the charge came from or what chemicals are inside. All we know is one terminal is high voltage, the other is low. And we have something the charge will flow through. It's not a mill, it's a resistor. Resistors look like this. They look like ceramic peanuts with stripes on them and wires like this. So we could have a resistor, but physicists are not amazing artists like me. So instead of a battery, let's draw this. A whole bunch of lines, some long, some short, alternating. And there's going to be a long line on one end that's high voltage, and a short line on the other that's low voltage. This is a battery. They could draw a resistor, but instead, they draw what I drew before, a squeal. This is a resistor. Sometimes you see a lamp too. A lamp, like a light bulb, is just this. So let's make a light bulb today instead. These are the circuit symbols for a battery and a lamp. Without the circle, it would be a resistor. So we almost have everything we need. We have a high elevation and a low elevation. The battery incorporates both these things, the place where the current comes from and the place where the current gets sent away or like recycled back. Basically, the current has to go back into the same battery. So the battery takes care of both those things for us, which is very nice. Then we have the place where the flow passes through and the energy is used up. We have high energy water, low energy water, and also use up here. If we have high energy charge, it'll flow in, and low energy charge will flow out. The energy is used up in here, which we'll talk about more in a while from now, later. So, what else am I talking about today? All you need to do is basically just make a river to connect them. So in physics, we always assume we have all the wires you could ever want. We always assume that they are a superconductor like copper. They're nice, thin, they never break, they're perfect. We assume we have infinite wire of no resistance, zero resistance. And to symbolize that in this diagram, it's just a line. So this is a wire. This is a wire. It basically just connects and allows the current to flow. The current charge will never lose any energy. It'll never slow down. Nothing will ever happen to it. It just perfectly connects without any losses at all. That's what we assume. Not technically true in real life, but it works for this assumption. We can use it as source of error for your lab, if you ever have a lab. Okay, what am I talking about today? This is a very basic circuit, just like this. Current flows out the battery into the lamp, then out of the lamp and back into the battery. It's always the same amount of current everywhere. It doesn't slow down going through the lamp. It loses energy, yeah, but it's the same amount of current. And it's the same rate. If 10 coulombs per second go in, 10 coulombs per second must come out. It's the same 10 coulombs. The only difference is it has less energy when it comes out. So that's really important. There's one thing in this picture that's actually not technically correct. It's not correct to say, oh, positive 10 coulombs per second will flow out the top, and then positive 10 coulombs per second will flow into the bulb, and then positive 10 coulombs per second will flow from the light bulb back into the battery. Why is it not correct to say that positive 10 coulombs per second flows like this? What's that? The charge is actually negative. Yes, that is correct. Protons don't flow, so positive charge doesn't flow. It's actually electrons going the other way. So if I say I have 10 amps of current, that's 10 coulombs per second flowing clockwise through the circuit, what's actually happening is 10 coulombs of electrons, well, negative 10 coulombs of electron are flowing counterclockwise every second. But it's the same thing. We can pretend positive charge is flowing. It's equivalent. This current is something called conventional current. The E's, you might call it electron current. Usually people talk about conventional current, but it's not technically affect much about the problem. Anyway, so that's great. Good job, us. One last thing to talk about. How do you measure the current? To measure these things, you need a multimeter. So let me just clean up this drawing, even though it's already amazing. Okay, so voltage is the potential difference across a circuit. It's across any part of a circuit. Since there's a difference, you have to compare 2 points. So let's say I have a magical voltage measuring machine, like so. Any machine that measures voltage will have two wires, two prongs, two terminals, two probes, whatever you want to call it, two things. And you gotta connect them. Where can you connect these two probes to find the potential difference, to find the energy change for any charge going through the circuit? It's kind of abstract, but let me see what you can say. Where can you connect this voltmeter to measure voltage to find the proper voltage? If you want to find the amount of energy lost when water flows from the mountain to the lake, you need to know how high the mountain is, but also how low the lake is. Hopefully that makes sense. You need to know the change in height. So we have to go from the mountain to the lake. The mountain is the highest voltage. That is right over here at the high voltage terminal of the battery. So that's one connection of the voltmeter. The other one is the lake, the lowest potential. That's when the current is going right back into the bottom of the battery, the low voltage terminal of the battery. Because as we know, the voltage always gets recycled. Let me tell you, the current always gets recycled. So we gotta attach here. To measure voltage, you take your two terminals and connect them to the two ends of the battery, which probably makes sense to you. I'll show you guys like a video in class of people measuring the voltage of a battery. It'll pretty much tell you like the exact voltage written on the battery, which makes sense. But what if you wanted to find the voltage difference at the two ends of your resistor or lamp? What would happen if it was connected like this? What's that, Daisy? It would be the same thing. This will also measure the voltage of the battery. I'll come back to this important idea later. The voltage difference from the high voltage terminal of the battery to the low voltage terminal of the battery is the same as the voltage difference or potential difference from one end to the other of your resistor or your light bulb. That's because, as I said, we assume the wires are perfect, ideal conductors that conduct charge efficiently with no energy loss at all. So basically, in my analogy before, the water flows from the mountain to the lake. But somewhere along the line, it passes through a little watermill. We assume that there's no energy lost at all from here to here, or from here to here. So all the energy that the water has at the top of the mountain, it has all of it, even right here, right before it hits the mill. And it loses all the energy, so it has the same energy right here on the other side of the mill as it does at the end, at the bottom of the lake. Basically, the potential drop, or the change in energy from mountain to lake, is the same as from right before the mill to right after the mill. All the energy is lost in the mill, and that's because the resistors, the wires are ideal conductors with no resistance. In physics problems like this, only resistors have something we'll call resistance. Resistors and lamps, which are basically the same thing, are the only things that resist the flow of charge or the current. So that's cool. That's how you measure voltage. So here's the last idea. If you want to measure current, you need an ammeter. This measures the flow of charge. It measures current, it measures amps. How can you connect it? Should you connect it the same way, like the voltmeter? What do you think? Don't be afraid to be wrong. Just tell me your ideas. Okay, here's the weird thing. If you did connect the ammeter like this, you connected a wire to your other wire. You allowed the current coming from the battery to split. I1 splits into I2 and I3. So this ammeter will measure I2, but I2 is not I3 or I1. It's separate, it's different. If you look at the picture, you might be able to figure out a mathematical relationship between the three, but for now, they're not the same. So this is not the proper way to connect a current and ammeter. You need to do something tricky. If you want to measure the current in a circuit with an I and ammeter, you need to actually break the circuit. So just take the circuit, open up the wire, and put an ammeter inside as part of the circuit. Just like the ammeter, just like the voltmeter, the ammeter will have two probes, two terminals, two sensors, two whatever you want to call it. But instead of finding the difference, like a potential difference, you just allow the current to flow through the actual ammeter itself. It's okay, it doesn't break the ammeter, that's what they're designed to do. The ammeter will not affect the current, it'll just measure it. And that's how you use an ammeter, which is an important topic for some people, for some applications of stuff. Yeah, this is supposed to be a pretty straightforward lesson. So the only important idea is I equals Q over T.